Yeah, so in this numerical, the question is you have to design a difference amplifier given that the op amp is ideal, the differential input impedance is 12k, differential gain is 32 dB, and common mode gain is 0. This is the first part. So let us do this first part. Let me mark this as the initial part. So one thing what we can do is we know that the differential input impedance formula is equal to 2R1 and that is given as 12 kilo ohms. So this is given as 12 kilo ohms, we can directly write what is R1. R1 is equal to 6k, that is R1 value. Now if you look at differential gain value, which is AD 32 dB, 32 dB is equal to 40 when not in dB scale. So, and that we know the formula for this difference amplifier. When your R1 is equal to R3 and R2 equal to R4, we have written this as R2 by R1, which is equal to 40, which again gives the solution that if your R1 is 6k, your R2 will be equal to 240k. These are the resistor values R1 and R2. Now, if you look at this specific op amp, it is given that this A is infinity, so that we can write this R1 as 6k and R2 as 240k. This is the first part of the design, right? Now if R1 is equal to R3 and R2 equal to R4, we know that the common mode gain will be equal to 0. Common mode gain will be 0 whenever we have this condition satisfied. Now look at the second part of the question. So the first part is done. We have, so 0 common mode gain is possible when your resistors are matched. Now the second part of the question says that if the resistors used are of 2% tolerance, determine the worst case common mode gain and common mode rejection ratio. So we have resistors. Now it is not talking about resistor values of R1 not equal to R3. The only difference is R1 and R3 say R1 and R3 should be equal, but the resistors are used with 2% tolerance. If that is the case, what can be the worst case common mode gain and common mode rejection ratio? That is a question, right? So for that, what we can do is first we should actually get the expression, because we never derived the expression for common mode gain when the condition is not met. Right, so that means if R3 by R4 is not equal to R1 by R2, the same condition what we have taken before. If R1 is not equal to R3 and if R2 is not equal to R4, even this ratio will not be equal. If this is the case, then what is common mode gain? This we did not derive. What is the common mode gain in this case? We have to derive this. We need to derive this. How will you derive this? So we have the circuit diagram with us. Say let's have the same circuit. There is no difference in the circuit diagram. I'm just taking it so that we can design this, right? So this is our V in 1, this is V in 2, and this is R1, this is R2. I'm just using the original expressions R3, R4, V out, right? Now in this case we know that the differential input voltage can be written as V in 2 minus V in 1. This is differential input voltage. Common mode input voltage can be written as V in 2 plus V in 1 divided by 2. This is how we write. Now if I can write difference and common mode gain, even I can also represent the input voltages. So how will I represent? I can represent input voltage as V in 1 can be written as VICM, or the input common mode voltage VCM minus VID by 2, and V in 2 can be written, this we already discussed, VCM plus VID by 2. This is how I can represent. Now the aim here is to derive the common mode gain under the condition that R4, when R4 is not equal to R1 and R4 not equal to R2 and R3 not equal to R1, common mode gain is not 0, and we are going to find the expression for that. How will you write the expression now? Now we know that V out is equal to so what is the gain at this terminal? So V out is equal to a sum of the gain in the paths V in 1 to V out and V in 2 to V out, right? V out can be written in that form. So how will I write? V out can be written as, so the voltage coming here, so the for the non-inverting input terminal, what we have is VCM plus VID by 2. Now for that signal, we have this resistor ratio, which is R4 divided by R3 plus R4, that is one term, multiplied by the non-inverting gain, which is equal to 1 plus R2 by R1, right? This is what is the gain for the non-inverting path. Now for the inverting path, plus what is inverting path gain? Minus R2 by R1 into this again VCM minus VID by 2. Is this clear? Can I get some response in the chat? What I have done is, I have marked V in 1 and V in 2 in terms of common mode and differential gain. Common mode signal and differential signal, and then I wrote the output expression. So output expression for the inverting terminal will be just the gain of this path R2 by R1. The output expression for the input, the gain for the input signal V in 2 will be non-inverting gain multiplied by this resistor divider. Can I get some response in the chat? All right. So I hope this is clear. Now what is remaining is, I'll just rewrite this in a better form. So it is R4 by R3 plus R4 into 1 plus R2 by R1, which is the gain of one stage, right? Now from this output expression, I will be writing the gain terms for common mode signal and differential signal separately, so that directly I can write what is the common mode gain and differential gain from this, right? So let me just mark this, because this is the non-inverting and the other one is the inverting gain. Now I have taken this common. This terminal, so R4 by R3 plus R4 into 1 plus R2 by R1 is common for common mode signal and differential signal. Now for the other, this is the complete gain term for the common mode signal VCM, right? Plus, now for VID, I have VID by 2 and minus VID by 2. So let me write it as VID by 2, and the factors here are R4 by R3 plus R4 into 1 plus R2 by R1 and plus R2 by R1, right? Because there is minus here, minus VID by 2, so it is plus. So this is the expression. Now if you look at this term, what I have is the common mode gain, because for the common mode signal this is the gain, and this term here is actually the differential gain, and the difference is only a sign, negative sign, right? So now I can write V out is equal to this quantity is common mode gain into common mode signal plus VID by so generally we write it as VID, right? So VID into this quantity will be VID into AD. This is how I can write, right? So that means in the differential gain you have to differential gain is with the factor half. That is how we have to take it, right? So from here you can see that this is ACM and this is AD. All right. Now going back to the question, in the question what it is given, it is given that in the design circuit, if the resistors used are of 2% tolerance, determine the worst case common mode gain and CMRR. Now we have the expression for common mode gain. Now we need to find the worst case common mode gain, right? Worst case common mode gain. So for that, what I'll do is I'll just write the worst case values of resistors, which can give you the worst case common mode gain. Right. So what is common mode gain here? ACM is equal to, let me just replicate the same expression here. All right. So this is the expression for output, and from this we can write the common mode gain and differential gain. Differential gain anyway it is not asked, right? So now what we have to do now. uh, in the previous case, if R1 and R3 equal to 6K and R2 and R4 is equal to 240K. This is the resistor value what we have. Now both the resistors have 2% tolerance. That means what is 2% of 6K? 2 by 100 of 6K is equal to 120 ohms, and 2% of 240K is around 4.8 kilo ohms, right? This is the tolerance value, and this is what we are expecting as a change in the resistor values. Now if you look at the factor here, common mode gain, we have the ratio of R2 by R1, we have the ratio of R4 by R3 plus R4, right? So generally or this can be further written as the ratio of R4 and R3, right? So what we do here is we go for worst case resistor values in the sense the ratio, say R2 and R1, R2 by R1, R2 and R1. So so what do you understand by worst case? The worst case value when R2 and R1 is equal, when R1 and R2 both are same, this ratio will be equal to 1. Ratio will not be equal to 1. R2 is 240K and R1 is 6K, right? So in general we can say in general R2 by R1 is equal to 240K by 6K. Now how to generate the worst case value? So worst case value can be generated two ways. One way is add 2% tolerance here and subtract 2% tolerance here, or the other way. That is how we generally do the worst case scenario, right? So in order to get the worst case values, all the worst case resistors values are written as R1 dash. I'll write it as R1 dash, R2 dash, R3 dash and R4 dash. And what I will do is in the ratio, one I will take plus tolerance and another I will take the minus tolerance, so that will give you the worst case values. So how will I write? Let me, if I am taking R1 dash as 6K, say minus the tolerance value of 120, then R3 dash what I will take is 6K plus 120, the other side, right? Similarly, since I have taken difference here minus 120, for R2 dash what I will do is 240K plus 4.8K, and for R4 dash I will take 240K minus 4.8K. This is how I will choose the resistor values, right? Now with this I can find the worst case, these things, R2 dash by R1 dash as 240K plus 4.8K divided by 6K minus 120 ohm, which will give you the factor closely equal to, can I get this value? What is R2 dash by R1 dash? Similarly R4 dash by R3 dash can be obtained as R4 is taken as 240K minus 4.8K, and this is 40, can you check again? 240K plus 4.8 and 6K minus 120. This is 6K plus 120 ohms. So this will give you another value. This is 40. Because this will come around 244.8K divided by 6K minus 120, it's around 5.88K. Yeah, so this will be 41.63. And what is this ratio? Yeah, 41.63. And what is the other ratio? 38.413. Right. So this is, see, what we obtain now is the ratio of the resistors, which can provide you the worst case ratios, right? Because if you want to find the worst case common mode gain, first we are finding the worst case combination of resistor ratios, and that we obtain now. Now with this you can go back and we can substitute these values in this equation, and then you can come up with the value of differential gain, common mode gain, and common mode rejection ratio. Yeah, so please calculate those values and check for these values by substituting appropriately in this equation. Alright, so what we have done is we obtained the worst case resistor values, and with that we are going to find the worst case common mode gain and rest of the stuff with the existing formula. Alright, so that's all about this. Please calculate and get the values, and we can have a check. Alright, welcome to this lecture of analog microelectronic circuits. So in the previous lecture we discussed about difference amplifier and instrumentation amplifier. So we concluded the class by developing the architecture of this instrumentation amplifier with 3 op-amps, and making the first stage input channels. Previously it was two separate channels, two amplifier channels were there in the first stage, and we saw that the matching of that is difficult, and later we come up to this architecture where we placed R1 resistor for both A1 and A2 amplifiers, A1 and A2 op-amps and that has given us a differential gain of R4 by R3 into 2R2 plus R1 by R1. This is the differential gain what we have derived. And looking at the two important advantages of this structure is, one is by introducing the first stage with a non-inverting amplifier, we are able to get high input impedance, and second thing is high differential gain, again because of the reason of two stages. Alright, so I hope you are clear to this point. So what we'll do in today's class is we'll look at a few numericals based on instrumentation amplifier and a difference amplifier. Alright, so let us first look at this question. The question is to design an instrumentation amplifier to have a variable gain. The requirement is a variable gain, and that gain should vary from 0.5 to 50, and it is also given that you can use a 50k potentiometer for this purpose. So yeah, the very first thing is the question is to design an instrumentation amplifier. Now from the previous class discussion, we know that instrumentation amplifier will provide a very high gain, but now the requirement of that gain is from 0.5 to 50. It is also given that you can use a 50k potentiometer, because since we know that the gain is variable, we definitely will be looking for a component which can help in varying this gain, and that is a potentiometer, and the value of the potentiometer is given as 50k. Alright, so how do we go about the design? We know the design equations, right? Design equations we know, the circuit diagram we know. So what we can do is, from yesterday's class we can take up this design equation, and the design equation is R4 by R3. The differential gain design equation is let me write for the first R1 plus 2R2 divided by R1. This is the first stage gain, into R4 by R3 is the second stage gain, right? This is the combined gain of the amplifier structure is this one, or this can be further written as 1 plus 2R2 by R1 into R4 by R3. This is another way to write the differential gain, right? Now the requirement here is this gain value should be in the range of 0.5 to 50. See, so the meaning is so if the differential gain is 1 plus 2 R2 by R1 into R4 by R3, this should range between 0.5 and 50. That means this quantity should be in this range. This is what we need to do, right? So since the question is to design, what you have to get is the values for R1, R2, R3 and R4 such that the differential gain can be varied from 0.5 to 50, right? So are there any thoughts in this? How can we proceed? Can I get some response in the chat box? Are you guys with me? Can I get some response? Yeah. Yeah, we have to, yes, definitely we have to assume certain values. So, since we have first stage and second stage gain separately, what we can do is one fair assumption is mm, say for example, let us assume that R4 by R3, which is this quantity, equal to 1. If this ratio is 1, if R4 by R3 is equal to 1, so if this quantity is 1, rest I can take it as 1 plus 2R2 by R1. This should range between 0.5 to 50. This is possible. Looks like it is possible, right? Because if I maintain R4 by R3 as 1, then 1 plus 2 R2 by R1, that quantity should be varied between 0.5 to 50, right? So that means if this should range between these two quantities in the sense, this will lead to say 0.5 is equal to 1 plus 2R2 by R1, or this will lead to this that 2R2 by R1 should be equal to minus 0.5, right? If I go ahead with this by assuming R4 by R3 equal to 1, that will give you the condition that 2R2 by R1 will be equal to minus 5, right? So is it possible to have a negative quantity or negative value for the ratio of two physical resistors? Is it possible? And we know that it is not possible. So what we can do now is one small modification we should do here. What is the modification required? We cannot assume that this R4 by R1, that ratio should be equal to 1, right? If we consider R4 by R3 ratio as 1, that will lead to this condition where this is something which is not practical, this range, right? So that means this ratio cannot be made equal to 1. I can try for this ratio lesser than 1, right? Why it is lesser than 1? Let us see. Let me assume that R4 by R3, instead of taking it as 1, let me take it as 1 by 4. If by R4 by R3 is equal to 1 by 4, this will lead to the condition that 0.5 should be less than or equal to 1 plus 2R2 by R1 into R4 by R3 is 1 by 4 less than or equal to 50, right? And if I solve this further, that means I should get two gains out of this, right? A minimum and maximum gain. See, let me write for minimum gain. Minimum gain is nothing but 0.5 here, right? So minimum gain is 1 plus 2R2 by R1 into 1 by 4 should be equal to 0.5. 0.5 is nothing but 1 by 2, right? So this will give you the condition that 1 plus 2R2 by R1 is equal to 2, or this can be further written as 2R2 by R1 is equal to 1, or this can give to the conclusion that 2R2 can be equal to R1. So this is one condition out of this, right? Similarly, that this is for the minimum gain. Now what I'll do is I'll just write for maximum gain. So what is maximum gain? 1 plus 2R2 by R1 into 1 by 4 is equal to 50. This is the second condition. This will give me the solution that 1 plus 2R2 by R1 is equal to 200, right? If this is equal to 200, yeah, so this is equal to 200. 1 plus 2R2 by R1 is equal to 200. Alright, so these are the two gain values. Alright, so what I have now is 1 plus 2R2 by R1 should be equal to 2, that is one condition, and 1 plus 2R2 by R1 is equal to 200, right? Mm, yeah, out of this we can get that condition too. Yeah, even if that is not really required, still I can write that. Yeah, so R2 should be equal to 99.5 into R1. All right, from that is also a condition out of this. Now, what we should do, since I need to vary the gain from 2 to 200, uh, or else what I can do is I can think in this way. So what I need is requirement is, what is the requirement? Requirement is variation of gain, from zero point 0.5 to 50, right? So in order to vary the total gain from 0.5 to 50, what I should do is I should vary 1 plus 2 R2 by R1. So this the above condition implies that this quantity should vary from what range to what range? 2 to 200. So in order to get a variation of gain from 0.5 to 50, 1 plus 2 R2 by R1 should vary from 2 to 100, right? So if 1 plus 2 R2 by R1 should vary from 2 to 100, and now we know that R1 is the resistance which is connected over here, right? So if I use a single fixed quantity resistance R1 here, I will not be able to vary this gain from this range to that range. So actually I should use a potentiometer. Now when I use a potentiometer, if I'm say because in the question itself it is given you can use a potentiometer of 50K. Now if I'm just using a potentiometer here of 50K, when the potentiometer is reduced to its minimum value, the resistance coming over here will be equal to 0, right? So that means I cannot just use a single potentiometer. Rather what I should do is I should use a fixed resistance along with a potentiometer, along with a variable resistance, right? So when I modify this, or how can I write this equation further is 1 plus 2R2 divided by R1 can be replaced with one fixed resistance and R1 a variable resistance, so that even if the variable resistance potentiometer value is 0, there will be a fixed resistance R1F. With that we can actually maintain, or with that we can actually vary the gain between the range from 2 to 200, right? So this is the condition now. All right, so now what I should do, first I can take say 1 plus 2R2 by say the variable potentiometer is at 0. If it is at 0, I will have minimum resistance here. When I have minimum resistance here, 1 plus 2 R2 by, when I have minimum resistance here, I can get maximum gain, right? There are two gain, one is low and another one is high. In order to get in order to get high resistance, I am using minimum resistance in the denominator. So this can be equated to 200. And the second case is 1 plus 2 R2 divided by R1F plus R1 variable. This will be equal to, or this can be equated to 2, right? So from these two relations you can get the values of R1 and R1F, R1F, R2, then R1V, and then we can solve it. So one thing here is, we know that R1 variable is given in the question, that 50 kilo ohm potentiometer, right? So by substituting R1V value as 50K, we can get the value of R2, R1F and the other quantities. Alright, so can I quickly get the answers for this? What are the values for R1? R1F is required, R2 is required, then R3 and R4. One more thing we know, R3 and R4. So R4 by R3 was equal to 1 by 4. That is a ratio what we have taken. What you can further do is you can try with different values as well. It is not mandatory that you have to always choose R4 by R3 equal to 1 by 4. When you choose the value of R4 and when you choose the ratio R4 by R3, see that that quantity is lesser than 1, so that we will not be ending up with a negative resistance requirement, which is not possible with the help of physical resistors, right? So this is a condition. Say if you have R4 is equal to yeah, if R4, say I'm taking 10 kilo ohms, into 4 will be R3. R3 is equal to 40k. That is one thing, right? So R3 is 40k, R4 is 10k, then R1V is 50k. Then the two quantities what you need to get is R1F and R2. Can I get the values for R1F and R2? R1F is 252.25. Yes, that is correct. 252.25. And what is R2? R2 is 25. Yes, it is 25.12 kilo ohms. Right. So these are the requirements, the resistor values, so that we can configure, we can get an instrumentation amplifier which can vary gain from 0.5 to 50. Right. So in order to get the variation from 0.5 to 50, the what variation what we have here is from 2 to 100, where 2 to 200 for 1 plus 2 R2 by R1, and for that we have actually selected a fixed resistance and a variable resistance, right? So this is how generally we do this, and yeah, since it is a design question, you can also show the circuit diagram. So in our case, I'll just draw the initial stage where we have two op amps, and from here we have a fixed resistance and we have a variable resistance. This is the first stage.